Okay, in this part 2, in a series of videos on line integrals, vector line integrals, we're going to be continuing with working through some examples that we started in part 1. So in part 1, we worked through A and B. We are now going to look at example number C. So in example number C, we want to find the work done in moving an object along the parabola x defined here in parametric form for t between -1 and 2 under the force field F. So I'm going to just make a little sketch here. So first of all, when t is -1, x is going to be -2, and y is going to be -2. So it means our point is going to be -2, 2. So if -2 is there, so we're going to start off there. We are told, well, we can see this is a parabola, and then when t is 2, x is going to be 4. X is going to be 4 from here, and y is going to be 5, which is 2 squared plus 1. So perhaps somewhere there, this is a parabola, so maybe something like this. Okay, so the details of the shape of this parabola are not very important in this case. It's just that we want to have a feel of what is happening. So this is our contour C. From part A and B, we said once we have the integral for the work done, which is going to be 6x squared minus 2y dx plus 3x plus y dy, then we seek to use the equations of the curve to express this integral in terms of one variable. The cases of A and B, we expressed everything in terms of x, where in this case our equation is expressed in parametric form. The parameter is t. That means we've got x in terms of t and y in terms of t. And so what we're going to do is we're going to rewrite everything here in terms of t. So we're going to use the parameter. The limits are already determined because t varies from -1 to 2. So that means if we write everything in terms of t, then the limits are going to be from -1 to 2. So x squared is going to be 4t squared. So this is going to be 6 times 4t squared minus 2 times t squared plus 1, which is y, and then dx is going to be, so x is 2t, dx is going to be 2 dt, y is t squared plus 1, so dy is going to be 2t dt. So this dx here is going to be 2 dt. Then we go to the dy term. So 3x is going to be 3 times 2t plus y is just t squared plus 1. Then dy is 2t dt. And then all you need to do here is to simplify. So removing the brackets, just simplifying to start with, this is going to be 24t squared minus 2t squared minus 2. Then in the second term, we have got 6t plus t squared plus 1. So this is still to be multiplied by 2t. Okay, and then if we multiply through by 2 here and by 2t here, then we're going to have so the first term is going to be 48. Maybe let's just do this first. So 24 minus 2 is 22, so, and then times 2, so that's going to be 22 times 2, going to be 40 squared, and then minus 4. And then from the second set of brackets, 2t times 6t is going to be 12t squared. Then we're going to have 2t cubed, then 2t dt. So if we write this in terms of the highest power first, we're going to have 2t cubed plus, it's going to be 56t squared, then plus 2t minus 4. So that's just the polynomial we have to integrate. So integrating this is going to give us t to the power 4 over 2 plus 56 on 3 t cubed plus t squared, and then minus 4t. The limits are from minus 1 to 2. And then if we plug these, okay, it shouldn't be a problem. So if we plug in t is 2, this is going to be 56 times 8 over 3. This is going to be 4 minus 8, so that's the first term. Then when t is negative 1, this is going to be 1/2 plus 50, it's going to be negative 56, so minus 56 over 3 plus 1 plus 4. And then if we punch this in the calculator, we're going to get 333 over 2. So that is going to be the work done along that contour, which is a parabola. At this point, just like I did in the part 1 video, I'm going to give you an opportunity to have a go at D. So if you'd like to have a go at finding the work done in moving an object along this parabola, t is varying from 0 to t3, and under the influence of the second force field that we have here, which is G. So if you just want to pause the video, work through this, and then when you continue the video, you can compare with our solution. Okay, we're now going to scroll down to our solution for the example D. Again, please note that if you have got any questions on any of the stuff we're doing here, please feel free to post. Would like to hear your comments. If these videos are helpful, again, we would appreciate to hear from you. Please do not forget to subscribe and like the video, and share accordingly for the particular topics you'd like us to do in mathematics. Then again, just feel free to post in the comment section. Right, so for part D, again, we have a parabola. It's defined by these parametric equations. T varies from 0 to 3. So when t is 0, the point is -1, 2. When t is 3, the point is 5 minus 7, which you get by just substituting there. This time t is the t squared is negative, so this is opening downwards. But the details of this are not important. It could indeed be like that, or it could be like that. All right, so that is our C. The differentials, so dx from here is going to be 2 dt, dy from there is going to be negative 2t dt, and our work done is going to be given by this, which is g dot dr. Then writing everything in terms of t, so our limits are now going to vary from 0 to 3. That's the first term and the second term. We'll further simplify, so the first term is going to give us multiply by 2 here is going to be 8t. This is 4 times 2, which is 8. That is going to be 6. Remove brackets here, that's what we're going to have, and then multiply through by negative 2t. That term is going to be like that. Then we can combine these two now. So if we start with the constant, it's going to be 8. Then the t terms are going to be 8 and 18, which is 26. The t squared term is minus 6 and minus 20 is minus 26. And then that's going to be the only t cubed terms. Integrate, substitute, and so our work done is going to be negative 174. All right, so thank you for watching. Part 3, we're going to then have a go at the last 2 examples, which involve, in one case, the ellipse, and then in the other case, a circle. All right, thank you.